Hi, well, pretty much any chemistry course you do is going to have a little segment on the development of the understanding of the atom. I have a video I've already done on Dalton. Dalton lived in the early 1800s, and he came up with some basics about the atom. Since I already have a video on him, I'll try not to talk too long here, but he revived the idea of an atom. It goes back to Democritus, back in the Greek, 2,000 years before Dalton and more. They had this idea that everything might break down into these little indestructible things called atoms. Dalton revived that, and he expanded on it. So he had this idea that maybe everything was made up of similar atoms, so that you have this kind of atom and this kind of atom, this kind of atom, this kind of atom, and that basically what we see are just different combinations of a finite number of atoms. So if you took everything and you melted the world down and you took all the different kinds of atoms, you would have a certain finite number of boxes, a certain finite number of atoms that everything boiled down to. That turned out to be a pretty good idea. And that these don't change from one to another. So you can't turn water into wine. Well, that's actually God can, but the way God does it is he rearranges things, I assume. I mean, he could create them out of nothing too. Water has hydrogen and oxygen; those are the atoms. Wine has a lot of other stuff, carbons. But anyway, that's not important right now. But atoms don't change into different kind of atoms generally. That they're these finite number of Lego pieces. That are, that's just those are the Legos that come with the Earth, and that the proportions with which these different atoms combine to each other are fixed proportions, 1 to 2 or 2 to 3, and so forth. Anyway, Dalton's the one who in the early 1800s came up with this idea of the atom. Now, so this second section, and I'm working off of Brown, LeMay, Burston, and Lemire's. Brown, LeMay, Burston, and Murphy's Chemistry, the Central Science. They have a section in which they talk about the development of the electron and the nucleus, as it were, that developing understanding of what these atoms actually are. Now, people knew about cathode rays. They turn out to be electrons. But I remember the name J.J. Thomson because in the town I lived, there used to be a factory called Thomson Electronics. And what they used to make there were computer screens. Now today we have these flat screens, which are wonderful. But they used to have these huge tubes. I mean, they were huge. you'd pull a cathode ray tube is what they were called, CRT screen. You'd pull it out of the back of a television at a junkyard. Not that I went to junkyards, but you pull it out, and this huge kind of tube, and what it used to be is it would shoot these little cathode rays or electrons, choop, 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 and it'd do it really fast, line by line by line. So the picture you'd see was basically this electron gun, cathode ray gun going, it would shoot these electrons onto the screen, and when it hit the screen, then it would light up, and all these little, it's like the pointillist painter Seurat. I don't know if you've ever heard of him, but every moment of a television show was basically this collection of points that a cathode ray gun, an electron gun, was shooting at the screen. Anyway, those were the days, and that we were there. But anyway, Thomson is the one that kind of discovered these electrons, as it were, that in fact the atom isn't the end, that there's more even beyond these atoms. By the way, a guy named Robert Millikan, this is all about 1900. Robert Millikan measured the charge and mass of electron. As it turned out that the charge of electron was 1.6 times 10 to the negative 19 coulombs. You don't need to know coulombs now, it's a measurement of charge. And that the weight, or not the weight, but the mass of the electron was 9.1 times 10 to the negative 28 grams. That's really small, 2,000 times smaller than hydrogen, in fact. So we're making some progress. About the year 1900, we're making some progress in understanding the atom. Now there's Ernst Rutherford. Ernst Rutherford enters into the stage. Now Thomson thought that maybe the atom was like a plum pudding. Now, I've never had plum pudding, So I might think of oatmeal and raisin. You've probably never had oatmeals and raisin either. But the way that Thomson had thought about the atom, he thought maybe you had this spherical pudding that had little plums in it, or I would say raisins in it. That the raisins are the electrons, and they're just kind of scattered around in the plum, which is the atom in general. But what Rutherford found out in his famous foil experiment, which foiled Thomson in 1910, is he found that generally, if you shoot, I think he was shooting alpha rays at this aluminum foil, and what he found is that most of the time, they just went right through. An alpha particle is basically a helium nucleus, 2 protons. You may not know what that is yet. Just ignore me. And what he found is that most of them went right through, and a few of them were deflected just a little. But just to be sure, he asked his assistant to check like the whole bounce back of the. He had it in a circle so that he could see where the alpha particles ended up. And what he found is that there were actually a few places where the alpha particle bounced back or to the side. And what he concluded is that the center of an atom must be, that most of an atom must be space. Most of an atom must be emptiness, but there must be a nucleus, maybe like the cell of an organism, that there would be a nucleus in the center, and then a lot of space, maybe electrons kind of hanging out in the space around this nucleus, and that most alpha particles, what they would do is they wouldn't hit anything. They would just sail right on through. But there would be some alpha particles that would hit the nucleus and bounce off and bounce back. And so Rutherford is the one, again, we're talking 1910, early on, came to the conclusion that in fact atoms were mostly empty space, but with a nucleus in the center, and then these electrons, somewhere in there as well. And so he would discover protons, which are the positive particles in the nucleus, in 1919. So now we have electrons kind of out in space, swirling around, as it were, a nucleus that is more concentrated, and that there are these positive particles in that nucleus called protons. And then in 1932, James Chadwick would discover that there are also some neutral particles in the nucleus called neutrons. So we have those are the 3 basic particles that you learn in middle school in an atom. You have electrons, which are negatively charged, protons, which are positively charged, and neutrons, which don't have any charge. A neutron walks into the bar and says, "How much does this cost?" And the bartender says, "For you, no charge." Okay, never mind. Okay, so that's the basic model, and Rutherford and Chadwick are developing it by the early 1930s. Radioactivity is also in this section of chemistry, the central science, so I'll mention them. Radioactivity is basically the spontaneous emission of high energy from an atom, and it was Henri Becquerel who discovered it while studying uranium. Uranium, of course, is something that used to be used in atomic bombs, because uranium is uranium-235 at least is radioactive. It emits high energy particles and disintegrates into lead, as it were. But anyway, so Becquerel discovered radiation, and of course you may know the name Marie Curie, Madame Curie, and Pierre, her husband, who studied radioactivity in those with Becquerel in those early days. Of course, Marie Curie died of cancer, just very cheery kind of thing, from her work with radiation. There are basically 3 types of radiation. Beta particles are electrons, basically. Cathode rays, beta particles, electrons. Let's call the whole thing off. You say electron, I say a beta particle. Okay, alpha particles, as I mentioned, are basically 2 protons, the helium nucleus, as it were. And then gamma rays, they don't make you into the Hulk. That's a nice thought, but if somebody shot you with gamma rays, probably it would just kill you. But anyway, gamma rays are not particles at all, but very high frequency energy. Okay, so back to the story. This isn't in chemistry, the central science, but it seemed like the story wouldn't be where we wanted it to be if we didn't end with Niels Bohr. who basically came up with what we might call the solar system model. This is not quite done yet. This model is not quite cooked, believe it or not, even though, you know, in middle school we thought, yes, I know what's in an atom. But the solar system model, this idea of a nucleus with electrons swirling around it like planets, even Bohr would learn that that's not quite right. But it's close enough, right? It's close enough for middle school. Soon it went to more of a cloud model, you know, that kind of like in Voldemort or the Death Eaters in Harry Potter. More of this kind of a cloud. Where is the electron? It's nowhere really. It's a probability field, as it were. It only takes on a location when you measure it, as it were. But that's for a later time. Well, I think that's pretty much what we want to say about the story of the electron and the nucleus.